In the name of Almighty God, I'm Mahsa Sankoshi, and today I want to talk about Proteus Virtual System Modeling or VSM. Microcontrollers are widely applied in the field of industry to solve engineering control problems. The increased use of microcontrollers makes microcontroller cores necessary for electricity-related specialty. A new simulation software package for microcontroller, Proteus Virtual System Modeling or VSM, is introduced for industrial and educational use. Proteus VSM combines circuit simulation, animated components, and microprocessor models to facilitate co-simulation of complete microcontroller-based design. Proteus VSM make it possible to develop and test designs before a physical prototype is constructed. The functions and advantages of Proteus VSM are introduced. The comparison of Proteus VSM Lab against hardware lab are deeply discussed. Proteus VSM is uniquely suited to teaching students about the design and operation of microcontroller-based systems. Why use Proteus VSM? We believe that Proteus VSM or Virtual System Modeling is a breakthrough product for electronic engineers, offering a new approach to development and debugging of embedded systems. Microcontroller and mixed-mode SPICE simulation with semantic capture and PCB layout. Proteus VSM was the first product to bridge the gap between schematic and PCB for embedded design, offering system-level simulation of microcontroller-based design inside the schematic package itself. Over 15 years later, Proteus VSM is still leading the field with more microcontroller variants and peripherals than any competing product, better measurement and debug tools, and a consistent focus on innovation. This simulation outlines some of the benefits to using Proteus VSM as an embedded prototype tool in your workflow. The first we want to talk about is flexibility. Proteus VSM provides a unique development platform for the embedded engineer. It allows you to specify a program, a hex file, COF file, or ELF, DW, ORF2 file as a property of microcontroller part on the schematic, and during simulation will show you the effects of the program on the schematic you have created. You can change your hardware by rewiring the schematic, changing component value for resistors, capacitors, and etc., and deleting or adding new components to the design. You can change your firmware in the IDE of your choice, and once compiled, test the new code on the new system at the press of a button. This gives you a total freedom to experiment with different ideas and to find the optimal design solution for project. The schematic serves as a virtual prototype for the firmware, and it's quick and easy to make changes to either. And the next concept is productivity. Typically, engineers spend as much time finding and fixing problems and testing projects as they do in creating them in the first place. This is an area where Proteus VSM excels. When you set a breakpoint in your code, the entire system stops when the line of code is reached. When you then single step, the entire system will advance, showing you the effects of the execution of that line of code and on your schematic virtual prototype. This makes it easier to work out where a particular problem lies and whether the software design or hardware design is at fault. Since the schematic is serving as the hardware, it is perfectly possible to divide tasks and for one person to develop the PCB layout whilst another uses the schematic as the basis for writing, testing, and debugging the firmware. This means that when the physical prototype finally arrives from the manufacturer, the firmware has already been completed and tested. Since the system has been debugged and tested in software, it will require fewer physical design iterations, and the product will therefore be market ready sooner. And the next conceptual is cost. As discussed above, Proteus VSM will save time and effort during the design phase and in the testing debugging phase. Both of these translate into cost savings for a project, and these savings multiply with each additional project undertaken. The ability to use the schematic in Proteus as a virtual prototype for firmware design and debugging improves the quality of the physical prototype. Less design iterations mean less delays at manufacturing and indeed lower manufacturing costs. Proteus comes equipped with a rich suite of instrumentation and analysis tools, from DSO to logic analyzer to I2C and SPI protocol analyzers. This makes it a mobile electronic workbench and reduces the need for expensive physical equipment. The purchase cost for Proteus VSM is itself extremely competitive, and Lab Center are committed to maintaining the highest level of price and performance. Now I want to talk about Proteus simulation about HC11 demo. Actually, the 68HC11, also abbreviated to 6811 for HC11, is an 8-bit microcontroller family introduced by Motorola Semiconductor in 1984, later from Freescale, then NXP. It descended from the Motorola 6800 microprocessor by way of the 6801. The 68HC11 devices are more powerful and more expensive than the 68HC08 microcontrollers and are used in automotive applications, barcode readers, hotel card key writers, and amateur robotics, and various other embedded systems. The MC68HC11OS8 was the first microcontroller to include CMOS EEPROM memory. What is a microcontroller class 11? One of the most powerful microcontroller ICs in 2024. A microcontroller is a programmed digital process with necessary peripheral. Both microcontrollers and microprocessors are complex sequential digital circuits meant to carry out job according to the program and instructions. And what is about architecture for HC11? Internally, the HC11 instruction set is backward compatible with the 6800 and features the addition of a Y-index register. It has two 8-bit accumulators A and B, two 16-bit index registers X and Y, a condition code register, a 16-bit stack pointer, and a program counter. In addition, there is an 8x8-bit multiply or multiply B with full 16-bit result, and fractional integer 16-bit by 16-bit divide instructions. A range of 16-bit instructions treat the A and B registers as a combined 16-bit D register for comparison. X and Y registers may also be compared to 16-bit memory operands. Addition, subtraction, and shift operation or can add the B accumulator to the X or Y index registers. Bit test operations have also been added, performing a logical and function between operands, setting the correct conditions code but not modifying the operands. Different versions of the HC11 have different number of external ports, labeled alphabetically. The most common version has 5 ports A, B, C, D, and E, but some have as few as 3 ports. Version D3. Each port is 8-bit wide except for D, which is 6-bit in some variations of the chip. D also has 8 bits. It can be operated with an internal program and RAM 1 to 768 bytes or an external memory of up to 64 kilobytes with external memory. B and C are used as address and data bus. In this mode, part C is multiplexed to carry both the lower byte of the address and data. And what is the implementation? In the early 1990s, Motorola produced an evaluation board kit for the 68HC11 with several UARTs, RAM, and an EPROM memory. The cost of the evaluation kit was $68. The standard monitor for the HC11 family is called Buffalo, a bit user-fast friendly aid to logical operation. It can be sorted in on-chip RAM, EPROM, or external memory, also typically EPROM. Buffalo is available for the most 68HC11 family derivatives, as it generally only depends upon having access to a single UART, SCI, or serial communications interface in Motorola parlance. Buffalo can also run on devices that don't have internal non-volatile memory, such as the 68HC11A0, A1, E0, E1, and F1 derivatives. And here you can see my simulation here with HC1, and you can download it from my GitHub master script and Proteus section. Thank you so much for watching my video until the end.